Okay, welcome back. It's my great pleasure to introduce the next speaker, Callan Spicer from King's College, and he will talk about moduli problems and birational geometry.
Great. Well, thanks very much for the invitation. It's a real pleasure and an honor to be here. So Fernando is my mathematical uncle, and it's great to see, well, so many members of the mathematical family that, well, I didn't know I had, so it's quite pleasant. I have 3 uncles, so yeah, this is great. I mean, I'm a much wealthier man than when I came to Rio, so this is great. I wish I had an embarrassing or funny story to share, but and I don't. But there's still like 2 days left in the conference, so maybe, well, we'll see. So anyway, I'm talking about some joint work in progress, and this is sort of a long-running and ongoing project with Michael McQuillan, Roberto Sfaldi, and Sebastián Velazquez, who will speak next. I guess the goal of my talk here is to sort of explain the perspective on moduli problems that birational geometers have, and maybe try to motivate some of the ways we think about this problem, or these problems. So I just want to start off with something very classical, and that's just the moduli space of curves. So this is a very classical object. So MGS, well, this is just going to be a set of stable morphisms of relative dimension 1. So here F is flat, proper. The fibers are stable curves of genus G. And I guess probably the most important, or one of the most important things about this moduli functor is that it's coarsely representable by a projective variety. So it's a DM stack. But it's coarsely represented by a projective variety. And this is somehow one of these great examples of a moduli space. And maybe I'll just start off by stating what our ambition is. So the ambition in this project is to do the same thing, or to have a similar story for foliations. The same thing for foliations. So to be quasi-precise, what I want is some moduli functor such that the fibers of it, or such that the values on some scheme S are going to be represented, or will give families of foliations. So this is, so maybe I want to be a bit vaguer. Nice families of stable foliations with some fixed numerical invariance. Okay, so let me make a few quick remarks on our grand ambition. So the first thing is that when I'm thinking about this moduli space, I want to allow the underlying variety and the foliation both to vary. So I want to let everything that can possibly vary in this setup. So both X and F vary. Well, I guess I hope F varies, but certainly X, I'm going to allow X to vary as well. So I was a bit vague. We have to decide what nice means. So we need nice, we need to decide what stable means. It's not clear. And we also have to decide which numerical invariants we want to fix are. So, and so we have at least three things we have to decide upon. But we don't want to just choose sort of silly definitions. We want to set things up so that M, and I guess this is the real dream, we want M to be coarsely represented by a projective variety. By or maybe if we're feeling a bit less ambitious, maybe even just a proper algebraic space. But again, the key point here is compactness. We want to set up this moduli functor so that we get compactness. So we want to, I mean, clearly foliations can degenerate in rather interesting ways, and in a few moments here, I'll try to throw up some examples of some interesting degenerations. We want to choose our definitions of nice, stable, and fixed numerical invariants such that these reasonable degenerations also appear in this moduli space. Okay, so this is our grand ambition. Maybe I want to, just to emphasize that this isn't such a crazy ambition. So maybe you might think, well, okay, this seems a bit far-fetched. Wouldn't the most natural thing to try to do is to first generalize the story of the moduli space of stable curves to higher dimensional varieties? So thankfully, this has been done. So there's been this huge project of research, so at least since the late 80s, involving lots and lots of people on generalizing the story of MG bar to higher dimensional varieties. So I want to spend a bit of time talking about moduli spaces of higher dimensional varieties. And the idea is that when we see how the moduli space of higher dimensional varieties is constructed, this will give us some good hints at what to do to construct these moduli spaces of varieties. Dimensional varieties. So this is sort of a summary section. Okay, so the first thing I want to remark on is stability for curves. So stable. What are stable varieties? Well, a stable curve. There are at least two ways of thinking what a stable curve is. On one hand, you can think of a stable curve as being the kind of curves which are given to you, which are stable in the sense of GIT. So this is one way of thinking what a stable curve is. Alternatively, you can think of a stable curve as just being one that is nodal, and the dualizing bundle is ample. And it's a deep fact that for curves, these two notions are equivalent. So if we want to sort of generalize the notion of stability to higher dimensions, we have to make a choice of which of these two paths to go down. Which of these two notions is the correct notion of stability in higher dimensions? So it turns out that GIT stability is bad. So this is an observation by Wang and Xu, is that GIT stability does not lead to a good moduli theory in higher dimensions. And in particular, what fails is compactness. So it does not lead to a compact moduli space. it even fails for hypersurfaces of high degree in P3. So it's really quite disastrous. It's almost like the first thing the first place where you think it might have a hope of working, hypersurfaces in P3, it actually breaks down. So GIT is the absolute wrong way to go about trying to construct moduli spaces of higher dimensional varieties. So what we're left with is to try to generalize this other characterization of stability in terms of it being nodal curves with omega C ample. Okay, so this is where I'm going to throw a lot of maybe arcane terminology on the board, but I promise I'll kind of define everything, but I'll try to motivate everything as well. Okay, so if GIT doesn't work, what was observed by Kolar and Shepard-Barron, well, they actually made two very important observations. The first thing was to define a stable variety. So X is stable. Well, what we need is we need that omega X is ample. Okay, so that's our positivity condition. Not so surprising. But we also need some sort of singularity condition. And the singularity condition that they settled on is called semi-log canonical. Okay. Part of what I want to do in this talk, my dream at the end of this talk is that you'll walk away from this talk believing that semi-log canonical was an inevitable condition, that we had to get to it, which is, okay, maybe this is a tall order. And so if I fail, please let me know. But I'm going to try to convince you that you would have been drawn inexorably to semi-log canonicity. I have to define it first. So that's one problem. So I'm going to define it, and I'm going to try to convince you that it was a natural thing to choose. Okay. So this is their definition of stability. There's another rather subtle point in the theory in higher dimensions, which I won't have much time to talk about in this talk, but I think Sebastián will touch on it briefly in his. Is that flatness is not enough in higher dimensions as well. So we say a family F to X to S is stable if two things happen. Or I guess three things happen. So it's flat and proper. Okay, that's reasonable. The fibers are stable. But then we need a third very subtle condition. And the third very subtle condition is that Kx over S is Q Cartier. So again, I don't want to belabor the point too much, but maybe I'll draw a red square around it anyway. That this is, for families of stable curves, this is immediate. A stable curve is Gorenstein, so the relative dualizing bundle of a family of stable curves is automatically a line bundle. But for varieties, this is not necessarily the case. You can have, you can take a quotient singularity, and you can smooth a quotient singularity in a way that the total space of the family does not have Q Cartier relative dualizing bundle. This is an absolutely critical point in the whole story, and it's actually where a lot of subtleties begin. But just to say that this notion of what constitutes a nice family is not at all obvious. Again, in higher dimensions, we need more than just flatness and properness. We probably need some additional conditions on the family. Okay, so like I said, my goal here is to try to convince you about semi-log canonicity. So what I want to do now is to give some examples to explain that, well, it's necessary, that we can't avoid singularities. And then my second, what I'll try to do then from after that point is to explain why this is a natural class of singularities. But maybe, well, actually, then maybe what I don't want to bury the lead too much about some of this stuff. Maybe I'll say that, so this is a theorem. Well, I guess the main force behind it's been Kodaira, but there have been a large number of names involved in this. And it's that actually, with this notion of stability, so stable families maybe fix n and v, so n a natural number and v a rational number, a positive rational number, then nv, if this is the moduli functor of stable families, so stable families in this sense, such that of relative dimension n, and kx, and such that the volume of the fibers, or so that the top power of the canonical bundle is v. So this plays the role of the genus of our variety. This is coarsely represented by a projective variety. Yes. Yeah, that'll follow from our definition of stability. So the fibers have relative, the dualizing sheaf of the fibers is ample, and so the relative dualizing sheaf is relatively ample. But yeah. And this is coarsely represented by a projective variety. Okay, so this was an immense undertaking. I think it's really only been completed in the past 2 or 3 years. But again, this is just to say that our ambition of trying to do a similar story for foliations isn't totally crazy. We have a good precedent, and we have a lot to build off of. But this is the state of the art for moduli of varieties. Okay, so let's look at some examples. So the first example I want to think about is, let's look at the following threefold: xy plus z to the n plus t to the k, and this is fibered over A1 with coefficient t, or with parameter t, and well, my map is just the obvious one, xyzt maps to t. And I want to put a foliation on this. Let's take my foliation, f, to be generated by the vector field x partial x minus y partial y. Okay. And so what we see is that xf over A1 is a family of foliations. Now, the general fiber of this projection is smooth, and so it'll actually be a foliation with 2 singular points. But on the central fiber, we get a singular variety. So on the central fiber, so x0 is just xy plus z to the n is equal to 0, and this is singular. So here we have an example of some smooth varieties degenerating into a singular variety. This is actually a quotient singularity. It's So this tells us that if we're interested in creating projective moduli of foliations, we at least have to allow quotient singularities under underlying varieties. Quotient singularities are inevitable, because here we have we definitely want smooth foliations to be in our moduli space, but in the boundary, quotient singularities will arise. So quotient singularities are inevitable. The next example is, let's take x to be xy plus zw is equal to 0. And again, this one will fiber over A1. And we're going to let our map be xy zw maps to xz. And then I will choose our foliation f to be defined by x partial x plus, say, lambda y partial y minus z partial z. Or maybe I want to, no, I'll do minus y partial y plus w partial w. Okay, this example is a bit crazier. This one, well, the central fiber, so x0 is a union of 4 planes inside C4. So it's x is equal to y, or x is equal to z is equal to 0, union x is equal to w is equal to 0. Union x, let's see here, w is equal to x is equal to 0, union w, or wait, we should get all 4 planes. X is equal to y, or x is equal to y is equal to 0, union y is equal to w is equal to 0. So we get something which is very non-normal. So this tells us 2 things. Well, on the general fiber, the foliation is smooth. But on the central fiber, the foliation becomes singular. Foliation is singular, and x naught is not normal. So this tells us that even if we restrict our attention to creating moduli of smooth foliations, even if that's all we care about, we're still in the boundary going to have to deal with singular foliations on non-normal varieties. So singularities are completely inevitable, even bad singularities.
Sorry, but the foliations are singular already, right? The fibers are smooth, but the foliations are singular.
Let's think. This should have an isolated singularity at the origin. Yeah. Actually, this one's even crazier. I mean, the leaves of this are algebraic. So you only care about smooth, algebraically integrable foliations. So now you think this is like one of the simplest class of foliations you can think of. To compactify it, you need to allow singular foliations on non-normal varieties. So again, these examples, the moral of this story is that to create compact moduli, you need to allow singularities, both of the foliation and the underlying variety. Okay, so, and like I said, the kind of singularities you have to allow are much more complex than just nodal. So whatever class of singularities we have to allow has to at least contain quotient singularities and nodal singularities. And this is where log canonicity comes in. Okay. Well, so maybe I want to pause here to see if there's any objections to singularities or not. If not, so what I'm going to try to do now is define log canonical, give lots of examples of log canonical, and then try to motivate this class of singularities. So again, hopefully these examples show that to create compact moduli, we need to allow singularities on the underlying variety and also of the foliations. And so then for the rest of this talk, I'm going to try to convince you that the kind of singularities we need to worry about are log canonical singularities, and also that they're a very natural class of singularities. Okay, so Carolina, in her talk, defined log canonical for varieties. The definition for foliations is very similar, but I'll recap it anyway. So let's say we have a foliation on a normal variety. X. I'm going to come back and talk about this assumption in a second. So F, a foliation on a normal variety X. So we define K of F is just a V divisor such that O of K of F is the dual of the determinant of the tangent bundle of the foliation. Now, if we let pi from x prime to x be any birational modification, we define the log discrepancy. So Carolina defined the log discrepancy for a variety, but we'll define the log discrepancy for a foliation. The log discrepancy as follows. So maybe I'll just move over to this board here. Keep things next to each other. So we define the log discrepancy as follows. What we can do is we can write K of F prime. Forgot. We need to assume that KF is Q Cartier. We define the log discrepancy. Well, we write this as pi star of KF and plus, well, some sum of A, E, F. So these two divisors agree everywhere except perhaps on the exceptional divisors. So E are the pi exceptional divisors. And we define the log discrepancy, AE, capital AEF, is AEF plus epsilon of E, where epsilon of E is equal to 0 if E is invariant, and 1 otherwise. So it's just the indicator function for invariance. So when the foliation is just the whole tangent sheaf, no divisor is invariant, so we get just 1 here, which was Carolina's definition of the log discrepancy. And so then we say that F is log canonical if AEF is bigger than 0 for all valuations E, all divisorial valuations E. And for any divisorial evaluation, of course, you can always extract it on some birational model.
What's F prime?
F prime, so yeah, so maybe I want to say if you have a foliation is uniquely determined on some by what it is on some dense open subset. So we can always take the strict transform of a foliation. So yeah, F prime here is the transform of F. So we just take the dense open subset where it's an isomorphism, and yeah, great, thanks. Okay, cool. Any other questions about this definition? So I'll run through some examples to hopefully give you a bit more feel for what this is. So I'll say that maybe also just as an apology. I mean, this is the definition of log canonicity. Maybe it's not very evocative because what does a log canonical singularity look like? I mean, it's determined purely in terms of these numerical invariants. It's a bit unclear what these things should look like. They're a bit mysterious from that perspective. And that's true. I think we don't know what a log canonical singularity looks like. They're just these things. But maybe I'll try to give you a lot of examples, though, to sort of maybe help you develop a picture in your mind of what kind of things these log canonical singularities really are. So let's think. So the first maybe or a very nice characterization of log canonical singularities for rank 1 foliations is due to Michael. So let's suppose that the rank of F is 1, and F is defined by a vector field partial. And let's let P be a singular point, or a singular point for the vector field. Well, we can look at the linear part of this vector field on the Zariski tangent space. So we get an induced map from on the Zariski tangent space to itself. And F is log, and so Michael's observation is that F is log canonical if and only if partial 0 is non-nilpotent. Sometimes, I guess, in the literature, these are called elementary singularities. So log canonicity is the same as being an elementary singularity. So for rank 1 foliations, there's a very clear and concrete way to view what they are, what these log canonical singularities are. Maybe another interesting set of examples comes from looking at cones. So Carolina, in her talk, gave some examples along these lines. I'll just reiterate them. So Mark 2. Let's say we have a variety. Let's say X is a variety, a projective variety with row of Picard rank 1. And inside some Pn, then the cone over X inside An plus 1, so this is some subvariety of An, or An plus 1, with a single singularity at the origin. And the cone vertex, this is log canonical. If and only if Kx is not positive. So Picard rank is 1, so we have a definite sign to Kx. So if X is Fano or Calabi-Yau, then the cone over it is log canonical. The third remark I want to make about log canonicity, and again, this is another way to produce lots of interesting examples, is that quotients of log canonical singularities are again quotient. So so I guess in particular, putting together point 2 and point 3, this implies that quotient singularities are log canonical. Any action of any group, yeah. Oh, yeah. Thank you, finite. Yeah. Actually, I mean, okay. There's a long story about quotient by non-finite groups, which is interesting in its own right. But yeah, let's say finite. I mean, I guess I believe in the existence of infinite groups. Okay, great. So putting these three things together, there's you have a very rich way of producing large kinds of examples which are log canonical. And you can check, just from these remarks, that all the singularities that appeared in the generations I was talking about earlier, they were all log canonical. Okay, so what I want to motivate now is why log canonical singularities are natural from the perspective of moduli. I'm going to give you a conjecture. If you can solve this conjecture, I'd be very happy. But I think it's pretty hard. So conjecture. Let's let X, F, S be a flat family of foliations. And suppose that KF is Q Cartier. Now fix a closed point S and S, and suppose that Fs is log canonical. Now, the conjecture is that there exists an open set containing S such that for all t in U, Ft is log canonical. So we expect log canonical singularities to form in moduli. This is one of the first reasons why log canonical singularities are natural from the perspective of moduli, is that they should deform. So once you have one log canonical foliation, everything nearby it should be log canonical. Okay, so maybe I'll call the conjecture, I don't know, LC deforms. So I want to make some remarks about this conjecture. And somehow understanding this conjecture is a big part of what we've been doing. So the first remark is that for families of varieties, this is known. So and a variety is just the foliation with one leaf, so it falls under your third conjecture. So this is known for families of varieties. This follows, well, I guess Kalamata proved a version of it, but then I think the full conjecture is essentially due to Kawakita. Their proof, though, cannot work for foliations. So the proof uses Kodaira vanishing in a big way. But there's no way to make Kodaira vanishing work for foliations. So their proof has absolutely no hope of working for foliations. But it's good evidence that it might be true. So in some sense, we need to find a new approach. So work. So maybe I want to tell you two cases where we know the conjecture is true. So theorem, the conjecture is true when, one, the rank of F is equal to 1, and, or 2, F has algebraic leaves. Okay, so I have 9 minutes left. I won't go into the proof of this conjecture, but essentially I think this is all the evidence we have for it. We have, it's true for varieties, it's true for rank 1 foliations, and it's true for foliations with algebraic leaves. If you believe some other natural conjectures, you can prove it in full generality. So I think there are good conceptual reasons for believing that this conjecture ends up being true. But again, I think this is a conjecture of fundamental importance. So I really encourage everyone to go out and give a crack at it. I think it's a great problem. So what I want to do then in the last little bit is explain an important corollary of this theorem for rank 1 foliations. And this is the reason why I'm so interested in this conjecture is because it has concrete implications for the geometry of the moduli space of foliations. So the corollary is that moduli of log canonical foliations is separated. Okay. So suppose we're in the following setup. So suppose we have two families of foliations over a fixed base S. And suppose that Fi S is log canonical for all S, and Kfi S is ample. So this is some kind of stability condition, and that Kfi is Q Cartier. So you should think of these three conditions as being some sort of stability condition on our family of foliations. Now let P in S be a closed point. Suppose that the dimension of S is equal to 1, so we're sort of a curve, and let S circ just be the punctured curve. Now, the point is that if we have that x1, f1, so the preimage over S circ is isomorphic. So is isomorphic to x2, f2 over this open subset on the base, then, in fact, they're isomorphic everywhere. So in other words, families of stable foliations are unique, so over a DVR, are uniquely determined by their value over the generic point.
I can't read. Are you assuming F1 or canonical or both?
Both Fi. So yeah, these are all i's. Yeah, so everything's log canonical. This is just exactly the valuative criterion of separatedness for the moduli functor. So Mark says verifies valuative criterion of separatedness. Okay. So let me, the proof actually is pretty straightforward. And we see why. I guess maybe I want to assume that, let's say the rank of F is 1 in this case. Although if we knew the full conjecture, we wouldn't need this condition. So the proof is, so by the conjecture, which again we know in the case of rank 1 foliations, we know that Fi is log canonical. So the first step, that Fi is log canonical. The second observation is that, well, because these two things are isomorphic on a dense open subset, they're actually birational. So there exists, by Hironaka, a way to resolve this rational map. So Pi is birational, and this resolves the rational map. Now, it's also easy to check because all the P exceptional divisors must be contained, or the Pi exceptional divisors must be contained in the fiber over P. This tells us that the Pi exceptional divisors are all invariant by the foliation. So I want to continue here. So now, by step 1, this tells us that K of Fw, where Fw is the transform of our foliation, or both our foliations onto W, is nothing other than Pi star Kfi plus Ei, where Ei is effective. And this is where we use log canonicity, is to guarantee that this Ei is effective. Now let's look at E2 minus E1. Well, this is going to be P1 star KF1 minus P2 star KF2. In particular, E2, so negative E2 minus, or E2 minus E1 is P1 nef. And also E2 minus E1, P1 star, is equal to 0. So by the Hodge index theorem, this implies that E1 minus E2 is actually effective. But we can swap the roles of E1 and E2. So actually we see that E1 is equal to E2. Okay, so then to finish up the proof, we just observe that we've shown that on one hand, we have that P1 star KF1 is equal to P2 star KF2. But we also know that Xi is equal, so because KFI is ample, this implies that Xi is just the proj over S of the graded section ring. But from the fact that KF1 and KF2 are equal, we see that these two graded section rings are actually the same. But we know that P star O M KF1 is isomorphic to O M KF2, and this implies that X1 was isomorphic to X2. Okay, so that's the proof. Again, the point here is that when we want to guarantee separatedness of a moduli space, log canonicity naturally arises. Okay, so I'll end there, but thanks very much for your attention.
Thank you. Questions?
Okay, so when you mentioned varieties, you mentioned semi-log canonical singularities. For foliations, there is no semi?
Yeah, thank you. Yeah, so yeah, I kind of swept this one underneath the rug. Yeah, so, okay, yeah, there is semi. Okay. So the challenge, I guess Sebastián will talk about this, is that we have to work with foliations on non-normal varieties. This is a bit of a headache because, well, there isn't really a good definition in the literature, so we've had to kind of cook one up ourselves. Mm-hmm. Roughly, the definition is that the variety is S2. The tangent sheet for the foliation is S2, and the normalization is log canonical. Mm-hmm. So you need some S2 condition and then a condition on the normalization, and that's where you get the semi from.
So that's necessary for compactness?
It's absolutely necessary for compactness, yes. Yeah, so semi really is necessary everywhere, but
okay.
to keep things slick, we dropped it.
Okay.
Further questions?
Thank you, Callum. So I have actually a somehow philosophical question, because I think when you were mentioning the moduli space of stable varieties, so okay, this will have their own singularities. But for instance, if you look at the moduli spaces of funnels, which have been very much developed now, the behavior is very different. Yeah. And then I wonder if, for instance, if you were interested somehow of building a moduli space of foliation, say on funnels, what would you expect? Which aspects of each theory do you think would somehow play a role?
Yeah, no, that's a really cool question. I don't have a clean answer for you. I guess I would think, okay, this is just a guess. I guess I'm being recorded, so I should be careful here. But my guess is that, I mean, so with moduli phonos, we can always compactify a family of phonos, and we can make the central fiber normal in these compactifications. But if we have, if our foliation is of general type, I don't see a way to do this without making the foliation badly singular. That's my guess. If we try the same trick that works for phonos, we're going to give the foliation very bad singularities. So my guess is that foliations of general type on phonos will sort of, philosophically, it feels to me that it's like varieties of log general type, where the underlying variety is phono, maybe. And so that seems to feel more like general type than phono in practice. But maybe there's some subtle influence, some subtle like phono perfume floating through it. I don't know. That's interesting. We should talk about this more, though. I think that's an interesting question.
Any further questions? So, and don't you expect to have kind of divisors popping out in the boundary, in the limits, so non-saturated foliations?
Exactly, yeah. So yeah, to be a bit more precise, yeah, what we really work with is we're not interested in moduli of foliations, but moduli of integrable distributions. Because yeah, in the boundary, I mean, yeah, so the other example that I didn't write on the board, but is you look at x partial x plus t y partial y. So when t is non-zero, you get a foliation, but when t is equal to 0, it has you know, a codimension 1 singularity. And this is unavoidable, so you have to. So yeah, we work with, we're looking at moduli of integrable distributions on non-normal varieties. This is really what our moduli problem is about.
Further questions? I was there. Why didn't you ask?
Sorry, just a silly question.
This is like the exercise job. I mean, yeah, it's really good.
What do you mean by flat family of foliations? Just sorry.
Yeah, so what I mean by a flat family of foliations, so let's say, okay, just to, okay, so when the rank of f, I guess Sebastián will probably talk about this a bit more in his talk, but when, say, the rank of f is 1, what I mean is that, okay, x to s is flat, tf is flat over s. And then, okay, I guess this is a distinction to your talk. What I want is I want tf restricted to xs to be reflexive. So I want the actual restriction to the fiber to be reflexive, not just, you know, we don't go to the reflexive hull. So it's a bit different than what you defined. But yeah, I really want the actual fiber to be reflexive.
Further questions? Comments? Okay, so we resume in 5 minutes with Sebastián talk, but before that, let's thank Callum again.